Okay, so as you said, whenever we try to design any antenna, the most important parameter that we care, it was this psi, which is shown here in equation 7.7a, and then often this array factor parameters, we describe them as polynomials in Z. But the polynomials in Z, maybe it is more explicitly or nicely represented that Z is this function. So it is e to the power j psi. So e to the power this whole unit that we observe here. Okay, so this is an important thing that we should remember. And as we saw the few examples we went over last time, they depend strongly on d and the beta. Now, all of these aspects, I think we discussed these. So I beg your. So one example which we could go over again, it has to do actually with this figure here. So I'm just saying a couple of words here. What is also important for us is that trying to determine which one is the visible range or which one is the VR. But this VR, we are in the, let's say, we are in the complex plane. And since we are in the complex plane, the roots of these polynomials, we need to use this complex plane because, for example, if we want to find all 5 roots of 1, we need to use the complex plane for reasons that we mentioned the last time. So, for example, z to the power 8 equal to 1, we can only find it in real domain 1 and minus 1, but the rest, they are in the complex plane. Now, what is tricky is that sometimes we might end up with roots which might be out of the visible range. So, for example, this design, if the d, which is the distance between 2 subsequent antenna components, if they have a distance of lambda divided by 8, and the beta is equal to pi over 4, apparently we notice that the visible range, it is between 0 degree and pi over 4, okay? Which, as it is shown here, one thing that is worth noticing is that this visible range, we are scanning it from theta equal to 0, we are scanning it from the vertical axis to the horizontal axis. Because as theta is changing from 0 and to 180, when theta is equal to 0, cosine is equal to 1. So pi over 4 plus pi over 4 is equal to pi over 2. That's why these directions, which are shown here in this path, they are drawn this way, which is they are clockwise. This is good. But now, what would be interesting is that we may have an antenna which has this distance, d lambda over 8 and beta pi over 4, but some of the roots, and let's not forget, so this is the z plane. When we say roots, we're talking about z's, values of z, which are shown here, these z's. It could be that some of these roots are out of the visible range. Okay, so we could have a root, for example, which is z can be 1, which would be here, z can be j, z can be minus 1 plus j. So what we can say here is that we can find a z root which is 1. It can be j. It can be, let's say, minus 1 plus j. If we have minus 1 plus j, that means that we have a root right here. We could have a root which is somewhere here, minus 1 minus j, and also minus j. So in case we find these roots for a given array factor, so let's say that we are given a certain array factor. We find the roots, we end up with these roots which are shown here. This, probably we can also find the root here, and all of these. Now the tricky thing is that as long as these other roots are out of the visible range, these will not be considered at all, okay? So these are some important fundamental aspects which we did not mention when we first discussed this topic, because it was better to first do some examples so that we understand each other better. So that's also some important aspect. Now I just want to skip these elements. So these are, again, this is an example which we have covered. So if you see what this one is about, we see that we have a specific d, lambda divided by 4. In this case, the kd is going to be 2 pi divided by lambda times lambda over 4, this will simply be equal to pi over 2. So this will be pi over 2 times cosine theta. So psi will be equal to pi over 2 cosine theta plus beta. Beta is 0, so this remains cosine theta alone. And then in this cosine theta, we will have, so wait a second, so when theta is equal to 0, cosine theta is 1, so then we get pi over 2, then z1 will be e to the power j times pi over 2, so z1 is equal to j. So this is what we find. So we can double check all of these elements, but okay, so we discussed the last time the Fourier transform method, which can be used to find the space vector. Now, to find the space vector, what is important? Well, what we notice here is that we are going to integrate over dz, but as we integrate over dz, here we have an expression which we can call this one also like a kernel. Okay, so this kernel, this is the equivalent of a filter. Okay, so in the signal and systems terminology or data filtering, these are like equivalent principles. So they are a kernel and a filter, and we know that whenever we take a Fourier transform, so the important topic here is that we may use a Fourier transform method to determine what is the space vector. Now, once we describe these in analytical form, which includes the use of some integral, the Fourier transform, it will be equal to integral of the exponent of the from minus infinity to plus infinity of some function in z, okay, times some kernel function which is equal to e to the power j kz dz. So once we do this integral, we're going to get a function which is equal to a function of k. So this is purely a Fourier transform of, so the space vector will be in fact the Fourier transform of what the source is. For example, if we have a line antenna where the current can be described as Iz, in this case, this is something like we have a line here, and we want to determine what is the space vector at some direction. Then the line antenna, it will be effectively integrating over all of these infinitesimally small components along the z. But once we do it, we simply have to look at the definition of the Fourier transform, and in principle, so this is the kernel that we were talking about in here. So this is the kernel, and then it looks like the space vector, it will be simply the Fourier transform of the original current. Now, in this regard, we can also say that this integral from minus infinity to plus infinity, this is in fact the integral from minus infinity to minus L over 2, right? Plus the integral in here, plus the integral from L over 2 up to infinity. But since the current here is equal to 0, these are directly equal to 0, okay? But what the usage, what is useful for us at this stage is that really the Fourier transform, it is an analytical integral from minus infinity to plus infinity. But since the current is equal to 0 from minus infinity to L over 2, effectively, this integral here, this is, so this integral in this range, it is equal to this integral, okay? So an argument of why this could be considered like the Fourier transform. And in this regard, what remains for us is that for simple current distributions, when we say simple current distributions, the simplest one could be the following. So let's say that the current from minus L over 2 to plus L over 2, the current, it can be a gradual increase in functions, okay? It can look something like this. And then we may need to take this integral. Integrating this expression, it is not that difficult. You can do it, and it might be a good exercise solving it. It's not something you should be afraid of. Secondly, the current from minus L over 2 to plus L over 2, it could also be a constant value, which could look like this. Then, whenever we are integrating in this regime, again, we can analytically, or it is one of the few functions which we can analytically calculate, and we can obtain the solution. So, let's see for a moment the excitation. So this is, let's go a little back. So we said that we wanted to calculate the space vector, and the space vector is described by this this function. And whenever we have a uniform current, for example, Iz prime is equal to Iz divided by L. This is a constant value, so this belongs, or this is somewhat, sorry, this is like this current here. If we take this integral, we find this expression. The space vector, it's equal to this. So it's going to be I0 times the sign divided by the argument of the sign. So it's like something like I0 sine x divided by x. For example, here we see the specific sectoral pattern, and in here we have that the SF vector is 1 in a specific domain from minus pi to 3 pi over 4, and then we may need to find what is the current distribution. Now, this analysis we're doing right now, if we compare with similar principles that we have seen so far, we are kind of, from f of x, we are finding, using the Fourier transform, we are finding the capital F of k. But then, similarly, we can use inverse Fourier transforms in this way, and from the space vector, we can also calculate the type of the current. So f of x, Fourier transform, we get f of k, capital F of k. Inverse Fourier transform, we can come back from this specific function to this other expression. Now, we are really taking the inverse Fourier transform because we can also notice that since we are integrating in the reciprocal domain, the integral of the limits of the integral, they are in the k space, okay? Because often this can be x-axis, a function, let's say if this is a sinusoidal function, we know that whenever we go to the k space, this will be, if this is a single frequency, this is going to be some specific frequency or some specific k0. If the function is a little more complex, then, so if this is the x-axis, we know that we may find out that we have several frequencies in the k space. But essentially here, so this is, we can come down with Fourier transform, or we can go from this domain to the, or we can call this one, these two, they are called reciprocal domains. Oh, sorry. So we can call, oh, I don't know how this happened. Sorry. Everything was undone. I did not expect it to go like this, but anyway. So these two domains between x and k, these are called reciprocal domains, which we can move back and forth with Fourier transforms. And now we notice that the inverse Fourier transform. So this is the current, okay, and this is the current as a function of z. If this is the current as a function of z, let's not forget. So this is the 0 that we obtain this from a constant space vector. This was the space vector, and when we calculate the inverse Fourier transform, we got this. And of course, this one is also a function of the, let's say, of the wavelength. And so here we can see how the space vector can be a pure cosine value or something which is not a pure sine value. One thing that we have, my last sentence, it was not a very clear one, but what we can say is that we've talked before in the class that whenever we do the design of the antennas, we often have, we measure experimentally, we measure the approximations of what the theoretical statements do. What we mean with this is that always we may have an antenna over which we might expect some nulls. So let's say that here, this is a null, so we should measure nothing here and here, but we still measure something because theoretically here we should get a 0, but often this may not be perfect. Similarly, in this case also, we may expect to get a pure step function in here. That is not always the case, okay? Now, the array factor of n element linear array of equally spaced elements, it can be defined or it can be used. So if we use the Fourier, if we use the Fourier transform to synthesize or to design a specific antenna, the initial mathematical apparatus is this. So we have seen these expressions before, okay? And then we can assume two different types of antennas where we have an even number of antenna elements or an odd number. Now, whether we have an even number or odd number, this is going to correspond to some principles that we have seen this before. For example, if you have an odd number of elements, and which this would correspond to n number of datas in the discrete space, or if you have n discrete values. Now, whenever we try to calculate the Fourier transform, often we observe a DC term. This DC term, it's a constant term which appears, which does not have any frequency equivalent. Now, regarding this, let me think for a moment. So any function f of x, this can be, maybe I should use a board here at this stage. But we're not going to describe, so any function, okay, I'm not very lucky with this. Any function of fx, this can be described as a summation of the an, this is from n0 to infinity, of cosine n omega, let's call it like this, and the zeroth term, cosine 0 is equal to 1, so we get something like a0, which is a constant term, plus a1 cosine omega t, plus a2 cosine 2 omega t, and so on. So we always have this omega frequency. This is the fundamental frequency. 2 omega is the integer multiples, 3 omega integer multiple again. But we have a DC term which appears for the fundamental frequency times 0. So this is a DC term. With DC term, this is simply mentioned like a not alternating current, but DC would just mean that it's a constant value. And in general, we say here the array factor is a periodic function of psi, so it must be repeated for every 2 pi radians. To satisfy the periodicity requirements for real values in the visible region, then we have 2k d is equal to 2 pi, where d is equal to lambda over 2. Okay, so apparently we have a constraint here, which we mentioned also in the previous few sessions, that in order to expect in practice the theoretical calculations, often we would like the distance between two antenna components, which should be smaller than d or smaller than lambda over 2. If d is larger than half of the wavelength, the patterns will exhibit undesired lobes. So this happens whenever this is larger. So we really want the opposite. Now, if d is smaller than half of the wavelength, the array factor in psi must be made pseudo-periodic by using fill-in functions, which is done in Fourier series analysis. Now, of course, this leads to non-unique solutions. What we mean with this, actually, we can describe this again later. But here we can simply, from here, we see what should be the excitation coefficients of a specific antenna. So now here the coefficients using the Fourier transform design, they should be given by these two expressions, 714b and 714c. Again, let me see for a moment. Yes. So what I can repeat here again is this aspect. So in the real domain, we have the current, which is flowing in some antenna. In this case, it can be a line antenna, which means that the current will be I, ampere. We could have an oscillatory current in an antenna component, the same way that the antenna components, we can see them at the signal station of some cell phone company. Okay, so this would be the current, which is flowing along this design. Now, this is the real domain. This is one thing that I want to make this clear. What we call this with the real domain is that this is X, okay, pure ECE. A real domain, it is measured in meters. Then we can calculate the Fourier transform of this current format, and we find what is the array factor up there in the space. So with the Fourier domain, we are obtaining some information regarding the possible directions of the K space. What we should not forget at this stage is the following. So in the wave equations, you remember that we have these e to the power jkx and e to the power j omega t. Now, k and x, they are reciprocals of each other. X is real domain, k is complex domain. Now, we said that if we have a current which is flowing over some wire, this is I of Z, so this is real domain. From here, we can, so this is the 0 here, and this is from minus L over 2 to L over 2. Now from here, we can calculate the Fourier transform, and we can find what is going to be the array factor as a function of theta, okay? So this is complex domain now, so we can say that the array factor, it is a reciprocal domain of the real domain. So this is complex domain. Because this is real numbers, these are complex for this reason. Now, the approach that we want to use is the following. We will give to a designer, someone who is going to design the antenna, he will learn from the persons that want a specific array factor or specific radiation pattern. What do you want the AF to be? He'll give to you, he'll say, he or she will say that the array factor will be something like this, which can be described as a polynomial which has some specific nodes. Then this array factor will be, so from here, we move this way with Fourier transform, then we can move backwards with inverse Fourier transform. So the technique here is that someone will give to an antenna designer the array factor. He'll say, this is the array factor. Okay, then find for me what should be the AMs, and these AMs, they correspond to the coefficients of the all antenna components which can be put into an array. Okay, so the question here, for example, we see that it's asking determine the excitation coefficients and the resultant pattern for a broadside discrete antenna element. When we have 11 elements with a spacing d equal to lambda over 2, and yeah. So given this specific d, we have also this this element, which is in fact, as we mentioned before, this is from theta from pi over 4 to 3 pi over 4. So this is a constant value, that's 1. And so this is the same equation, this is the spectral function. We need to integrate, and the integral of a constant value which is equal to 1, it is relatively easy. Okay, so it's equal to this actually. All the components of the excitation factor of the antennas will be as shown in here. Then this was the Fourier transform technique. Sorry, keep. Then we have this other method, which is the Woodward-Lawson method, and we may skip this one. So it's okay. I'm just wondering. No, okay, we skip this also. We're not going to do this approach. It's Woodward-Lawson. We're not going to go over this synthesis. We have conducted quite a few different syntheses. Here we have the Taylor series, line source. This is an interesting analysis of how an antenna can be designed, because this is also one of the types of designs which brings to mind common functions which are often used for from the most basic mathematics you have taken, starting from calculus 1. Taylor series, Taylor line source. Okay, so I believe this will be all with regard to the techniques that we can learn from chapter 7. Okay, no, this will skip this also. Okay, this is all. Then we finish with this one. Sorry, no, not stop recording. I should stop. Share the screen.
Professor, you just clicked yes.
Okay, yeah, okay. I forgot it was here. Stop. Yes. It was in here. That's good. Now unpin yourself from the main screen. This is really some interesting design. Okay, then now let's have a look at some antenna design. But so this antenna design we'll go over right now. They will be similar to the examples we covered also in the last session. In fact, now, yeah. You can see this part. So let's assume that we have an array factor which is in the order of, or it can be described like this, z times z cubed minus 1. Now, as you can see here, we have an array factor which is a polynomial in what order? This is an array factor which is a polynomial to the fourth order. And since this is of the fourth order, we may expect to have what number of the antenna components. So from this one, we could expect that the number of antenna components to be around n equal to 5, because we have a polynomial of the wait a second, of z to the power 4. Now, we can expand this one as z to the power 4 plus 0 times z to the power 3, because this is z to the power 4 minus z. Then plus 0 times z squared plus plus 1 times z plus 0 times z to the power 0. So now we see here that the polynomial in the fourth power of z, number of antenna elements is expected to be 5, and then here we can have that, we see that we can observe, wait a second, A1 is 0. So these coefficients, we go here, A1 times z to the power 0. This is A2, A3, A4, and A5. So since we have 1, 2, 3, 4, 5, so these are all the antenna components put in order. And what we would like to do, actually, we would like to have the excitation coefficients of the antennas at the edges to be equal to 1. Because this would be one way how we define the normalization. We're lucky, those coefficients are already 1. But if we are to write them down, we get here A1 is equal to 0, A2 is equal to 1, A3 0, 0, and 1. These are 0, 0, and here it's 1. So it looks like we have the second element and the fifth element. They are active parts of this antenna design, and another two. Actually, do we have any mistake here? Can you have a look? So here.
Professor, I think the A2 is minus 1.
It's correct. That's why it's minus 1. So that's what I was trying to notice. But here, this is minus 1. So if this is minus 1, we can also write. So this is A5. It's equal to 1. A4 is equal to 0. And A2, it's equal to minus 1. Or it's also 1 with a phase angle change of 180. Okay. So what this means? This means that we can have an excitation of the current in this element with some sinusoidal wave, and in this other element, it can still be the same sinusoidal wave, but it can be 180 degree out of phase with respect to the other one. So these two statements are equivalent. So you can choose either one, but you are right. It should be minus 1. So if this is the case for this specific antenna array component, we found what these elements are, and now what we can try to determine is also where we are going to observe the nulls. Okay, so this is also an important factor. Now, in order to determine the nulls, we should find where this array factor is equal to 0. In fact, we can say that in order to find the zeros, can this z, so this is z times z to the power 3 minus 1, this is 0. Now, if either this one is 0 or this one is 0. Now, can z ever be equal to 0?
No.
That is correct. So this can never be equal to 0 because we should not forget what z is. Z, it is e to the power j psi. And psi, this was equal to kd times cosine theta. And cosine theta, it is this angle theta, which is measured with respect to the z-axis. Often, we have to select some orientation as a reference. We do select the z. So in this case, this is kd cosine theta, which is this, plus beta. Okay. Now, and then this whole thing, this is equal to, and actually this z, e to the power j psi, it is equal to, or it can be represented as any number which can be found in this complex domain. And this never gets equal to 0. So we always move across this path, okay, this is sure. We never end up in 0, because e to the power j psi, this is going to be equal to cosine psi plus j sine psi, and these two are never simultaneously equal to 0. So here, this is never equal to 0, but then we expect zeros to be here, which means that z cube can be equal to 1. And if z cube is equal to 1, we need to find what is z1, z2, and z3. Now, the root of this one, we expect the roots to be here. So we have 360 degrees divided by 3. This is equal to 120 degrees. And if you want to check about that, we have e to the power j times 2 pi over 3, okay? So this is one of the numbers. If we raise this one to the cube, this is equal to e to the power j times 2 pi, which is equal to 1. So we confirm that one of the z's, it can be 120 degrees. Now, this is the case, and let's assume that beta is equal to 0, so that if beta is equal to 0, we can have e to the power j kd cosine theta well, this can be so in fact we have 3 different roots. For each one of these, we should have if we use for e to z1 equal to 1, this is going to be equal e to the power j times 2 pi, and then let's see if we have some specific value d. Actually, you can come up with any d. So you can pick up a d, which can be, for example, lambda over 10. So if we pick here lambda over 10, then this will be 2 pi over lambda, which is k, times lambda over 10 cosine theta is equal to 2 pi. Then the lambdas will cancel out. We have the 2 pi, we cancel out the 2 pi, and what do we get then? We get cosine theta is equal to what? Is equal to 10. What can we say in this case? So we get no null in this for this specific value. In fact, d, we selected it relatively small. Let me think for a moment. So here we get the kd. What did we get for kd? We got pi over 5, right? Yes, I mean that's true. Pi over 5. Okay, so we got no null here. Let's see the other z2. Z2 equal to e to the power j. What is this? 2 pi over 3. Pi over 3 is 60 times 2, 120. Okay. Then this should be equal to e to the power j kd cosine theta pi over 5 cosine theta. Let's see if we have any null here. So this means that these two arguments should be equal to each other. So we get here 2 pi over 3. Do you see any null or maybe not? Times cosine theta, pi is cancelled out. And then still we have no null apparently, because the cosine theta will be equal to 10 divided by 3, right? So apparently we have no null, and I don't see much. 10 divided by 3. No null again. And Z3 is going to be equal to e to the power j times 2, 4 pi over 3, e to the power pi over 5 cosine theta. Is there any? It looks like we don't have any chance, right? What can we say? Do you expect any null here? So just by increasing this side of the idea. No, right? Okay, so it looks like no, we're not going to have anything. So because we get here cosine theta will be equal to 20 over 3. Cosine theta will be equal to 20 over 3. But how is it possible? Here we got the 0 and 3 here. Yeah, this is also larger than 0. Now, we picked up a bad, for the given values that we have, we pick up not the best d. If d is equal to lambda over 2, so if we select here lambda over 2, then, say it again. You said something?
Vetëm për bën barat në lënda mund të dalin nga aty. As me lëndat e gjitha mund të ketë sistem.
Asnjë asgjë, vetëm nëse do është lambda.
Po. Sepse del kosinus theta baras me 1 kur bën lambda.
Okay. Because KD is equal to 2 pi over lambda times lambda over 2. So we get here pi, sorry, this is right. So even if it is lambda over 2, so we can say we get pi. So we get pi times pi, so it should be even larger than pi over 2, right? Sorry, it should be larger than lambda over 2 apparently. But in this case, we have pi cosine theta. Wait a second. Who can correct me here? So this is pi cosine theta should be equal to each one of these three numbers, right? It should be 1. Sorry, no. So the exponential of pi cosine theta, this should be equal to exponential of j times 0. In fact, it can be even j times 0, because 1, it is equal e to the power j times 0. It's also e to the power j times 2 pi equal e to the power j times 4 pi. And even the first value, if we set this one e to the power j0, we can expect here that pi cosine theta equal to 0. This implies that theta is going to be equal to pi over 2. Okay, even here, in fact, so we kind of missed this one, but we should not have missed this. So even when z is equal to 1, when we have kd is equal to pi over 5, we should get this one, I believe, right? So this is the second part, but it looks like even in the previous case, for z equal to 1, so let's think for a moment. So let's consider d. We are redoing the previous part, right? Lambda over 10. this is 1 over 10. KD, it's equal to pi over 5, then exponential to the power j, pi over 5 times cosine theta. It should be equal to 1, or it is equal to e to the power j times 0. The angle is 0 degrees. Then we have the pi over 5 times cosine theta. It should be equal to 0. So that means that we can always have a null at pi over 2. Okay. Okay. So we found at least one null for even for the case when d it was equal to lambda divided by 10. Even when we have this other lambda, we can still find something similar. Okay. We can pick a different example. Or if you want, we can have a very short break meanwhile.